Hi, my name is Eric Moser, and I'm here to present the work called Modeling of a Hierarchical Supervisory Control Industrial Process for Fault Diagnosis. This presentation is divided to introduction, the methodology, discussion, and conclusion. We can find two-level control systems in industry. At the lowest level, we have continuous timing, such as proportional integral derivative control that is implemented to guarantee that the system behavior follows the specifications for transient and permanent regimes to a reference signal. In the higher level, a supervisory control strategy is implemented to ensure safety specification for both routine and non-routine operations. However, both levels of control strategy are designed considering the nominal behavior of systems components, and thus the consequences of fault events are usually not taken into account in the project of control logic. At this point, fault diagnosis is an important part of the safe operation of industrial systems since the occurrence of a fault event can lead the system to unpredictable behaviors. We are dedicated to following the plant model behavior using a diagnoser, obtained by labeling the system states as fault-free or not and computing an observer of the labeled model. If the diagnoser reaches a state with only faulty labeled states, the fault is diagnosed and a signal is sent to the system operator. In this paper, a modeling strategy to represent both the fault-free and the post-fault behaviors for a common industrial process is proposed. To do so, we modify the component models of the system used in the supervisory control project to introduce the fault event and the post-fault behavior. The global post-fault behavior of the system is computed by the interaction of the supervisory control logic already computed in the project stage. In this work, we use a real industrial process as a case study. Discrete event systems, as used in this work, present a discrete set as a state space, and the transition is driven by events. Considering systems like this brings a series of advantages, such as simple modeling and integration with other control and observation techniques. One of the formalisms used to represent language generated by discrete event systems are automata. Using this tool, the language is represented with well-defined rules, with easy representation of the system using a state transition diagram. The states are represented by circles. The transition between the states is the events, and are represented by arcs. The initial state is an arrow without origin, and the marked states have double concentric circles. The system considered in this work is a pilot plant manufactured by Smart Industrial Automation installed at the Federal University of Santa Catarina for training and research of advanced control and automation technologies. The industrial process is used for controlling the liquid level of a tank. To do so, it consists of a pump that supplies liquid to the tank and a pneumatic valve that is used to regulate the liquid level of the tank. The instrumentation of the system is composed of two intelligent foundation field bus sensors, a level sensor in the tank, and a valve position sensor, which are used to implement a distributed PID control system. In addition, the PLC also receives the signal from a selector switch implemented on a human-machine interface panel, and it can control the pump. The supervisory control for this system is designed to prevent underflow or overflow of the tank due to misoperations. Thus, the supervisory control limited the system to the nominal behavior of the system components. Thus, if a fault event occurs, its detection must be computed to allow the replacement of functional device. The fault behavior is not desirable since it causes deterioration of equipments. The proposed method aims to adapt the system component models for diagnosis purposes. The model used in the project of the supervisory control proposed in Oliveira for the system are present in the sequence. The system is composed of 7 modules. G switch models the behavior of the selection switch. G levels models the level of liquid in the tank. G pump models command event to the pump accordingly to changes in the tank level. GPP models the preemption of the level transition by pump events. G-valve models the valve behavior. GPV models the preemption of the level transition by valve events. And G-flow models the flow of liquid in the tank. Let's take into account the valve model. In the valve model, VOpen and VClose symbolize the command event to open and close the valve, respectively. The event vregul is used to represent the switching of control from the supervisory to the PID control. For these systems, 4 specifications are considered to ensure safety constraints: directive action on the valve, directive action on the pump, the interlock between pump and valve, and the operation modes. In general, the supervisory control project is done considering the models of the previous slide. In this context, both control commands and their consequences in the systems are modeled as a single event. For example, event VOpen of the valve model models both the control command to open the valve and its consequence opening. However, if the valve is stuck closed, the control command to open will be sent the same way, but the valve will not physically open. Thus, the first step to solve the problem of fault diagnosis for industrial processes is to separate events into control commands and their physical consequences. In this work, we consider that the valve of the system present can fail and it stuck closed. This fault was chosen since the valve is used as the actuator to regulate the liquid level. We also chosen this type of fault due to the mechanical characteristics of the valve. The modified model for the valve is presented. In this model, events CVOpen, CVClose, and CVRegul represent the command to open, close, and regular the valve that can be sent from the controller. Events open, close, and regul represent the physical consequence of the valve due to previous command sent by the controller CVOpen, CVClose, and CVRegul respectively. We use event F to represent the fault event, and we consider that the valve can fail after any command, which leads the system to states VTC. The modifications to the valve are simple to make, but the fault is not diagnosable because there is not enough information considering only the valve dynamics. It's necessary to take into account the interaction of the valve's post-failure behavior with the other components of the systems. We start by replacing the valve events in the G-flow model with the open, close, and regul events, since only the physical behavior of the system components is described in G-flow. On the other hand, the valve preemption model GPV receives the command event CVOpen, CVClose, and CVRegul to represent that at least one control command is always taken on the valve between 2 consecutive level transitions. In the supervisory control framework, the specifications are used to compute the supervisor, which can disable events to assure that the closed-loop system satisfies these specifications. Thus, in the specifications model presented, valve-related event VOpen, VClose, and VRegul are replaced by CV Open, CV Close, and CV Regule, respectively, since only these events can be disabled by the supervisory controller. The next modification is to change the operation modes models. As the operator can stop and start the system accordingly to the original model, the global plant model is not diagnosable yet. We propose a new model to represent the change in the system operating modes. Two hypotheses are made. The system initialization occurs after the USP event, and the stop event models an unsuccessful initialization. It's important to remark that the diagnosis procedure is passive and runs in parallel with the controlled system. The modifications proposed in this paper do not interfere with the closed-loop system behavior. In addition, the language generated by parallel composition of all systems is diagnosable with respect to the fault event F. In this paper, a modeling strategy for fault diagnosis is proposed. The post-fault behavior for the supervisory control project is modeled. The global plant model is diagnosable, which shows that the proposed method can be applied to industrial processes. The authors are now pursuing other types of failure that may occur in the system and in other diagnostic architectures. This work was realized with financial support from the Human Resources Program of the Agência Nacional de Petróleo e Gás, supported by resources from investment by oil companies. Thank you also to all the collaborators of this work.